This is our first video for Chapter 1. I will try to keep these videos fairly short, however you'll notice that they'll get longer as the material gets more complex because I will try to give you more examples. So we're starting with Chapter 1 in the textbook, and in this video we're going to be talking about standard units, dimensional analysis, and significant figures. So we're going to talk about standard units to begin with. We are looking at length, mass, and time. Now this week we're a little compressed because we're starting the class and we still have to get in enough information for an exam. But luckily the information that we're going to cover this week is not nearly as complex as the rest of the semester will be. So we are going to talk about the standard units that we are using in this class. We're going to use a unit system called MKS. It is part of the metric system and it stands for meters, kilograms, seconds. So our length, our unit of length is going to be meters. When we write this for a unit, it's going to be abbreviated with a lowercase m. Our mass is going to be given as kilograms. So when we write this as a unit, it's a lowercase kg, and our time is going to be represented as seconds. Now you'll commonly see also in the metric system a system called CGS. I'm going to mention that here. This is not what we need for our problems. When we start a problem in this chapter, we need to make sure that everything comes back to our MKS units so that it plays nicely in our equations. CGS stands for centimeters, grams, and seconds. That's not the system that we're using, but that is a different system that is within the metric system. So length, we all know, is defined as distance. We are all familiar with length. When someone asks you, how long was your walk? You know that they're talking about the distance that you walked. Or when someone asks you, how long is that piece of string? You know that you're going to be measuring a length. Mass is a little bit less clear. Mass is not the same as weight. We often use it interchangeably in our daily lives, but it is not the same as weight. Mass is the amount of matter that is in something. It's the amount of stuff that's in something. So, for example, your mass, the amount of stuff that's in you, doesn't change if you go up on the tallest mountain. However, your weight might change because the pull of gravity on you is slightly different on the top of the tallest mountain. Your mass won't change, assuming that you're eating the same and exercising the same, if you travel to the moon. But your weight will change because your weight is how gravity pulls on that mass. Weight is actually a force. Mass is not. It's the amount of matter in an object. Time is something we're also familiar with. So we define time in terms of seconds, minutes, hours, days, months, years, and so on. These are going to be our standard base units. Everything that we do in the first several chapters, and probably all of this semester, is going to be based on these three quantities, length, mass, and time. We can put them together to get into more complex quantities. So these are our base quantities. That means that they're broken down, and they can't be broken down into anything more simple than this, but we can put them together to make things that are more complex. For example, speed. When you're talking about the speed of your car, whether it's in miles per hour, so we write that as mph, but really it is how many miles you went over how many hours it took you to go those miles. That's the way that there's a per in the middle, miles per hour. The per is the division sign. We say meters per second. How many meters did you travel in a given amount of time? So a speed is telling us the rate of travel, the rate of distance. So it's distance over time. We'll be also introducing concepts like velocity and acceleration. Speed is how fast you're going, but it's just a number. A velocity has a speed, so it's how fast you're going, but it also has a direction. but we'll get back to that later. Next, we have dimensional analysis. So sometimes we need ways to check and make sure that what we're doing makes sense. And the more complex we get in our physics, the more we need these little checks and balances. So dimensional analysis is the first of these types of checks that we're going to be introducing. I'm going to I'm going to erase my little CGS here for a second because I want to build onto this list that I've made here. So I have my quantity, length, mass, and time, the units that it's in, meters, kilograms, and seconds, and the abbreviations for those units. I'm also going to write down so we've already written down when I've said the quantity. The quantity is the dimension, the type of dimension. So when I'm talking about dimensional analysis, I'm talking about the type of quantity that it is. Length is a type of measurement that we make. So we're going to call that a dimension L. Mass is another type of measurement that we will make, and we're going to call that a quantity M. And then time. So we can check equations. For example, the speed or velocity, when we're coming up with the speed, the number for the velocity. Velocity is represented by a v. Speed is also represented by a v because it's the number that goes with the velocity. We would say that it has the dimensions of a length over a time. So we can do dimensional analysis. I prefer to do unit analysis, where I'm actually looking at which units are left in my MKS system, but some people like dimensional analysis. What I would suggest though is that you pick one or the other and don't mix them up because there's a lot of letters to get confused. So dimensions can be treated as algebraic quantities. What that means is they represent a variable. So L represents some kind of distance that you would plug in, and T represents some kind of time that you would plug in. I can check equations and see if my dimensional analysis works out because, so velocity we've said is L over T, and that would give me units in that of meters per second. Acceleration, we'll find, is a change of velocity with time. So it is speeding up or slowing down of your velocity. So it's length, the distance, over time, and that whole thing is divided by time. So when I write that as a proper fraction, it looks like length over time squared, because this, L over T is the same thing as L over T. This should be a T on the bottom, not an L. My apologies. So it's L over T times 1 over T. When you're dividing by something, it's the same as multiplying by 1 over that thing. So we end up with acceleration looking like L over T squared. That would mean its units are meters per second squared. I'm going to put up a clean slide here in a minute, and we'll go through an example so that we'll look at how how dimensional analysis helps us to check our equations. So using the quantities that we've introduced so far, we have length, we have mass, we have time, I've talked about velocity, and I've talked about acceleration. So I want to do velocity times time, and I want to know what those dimensions are going to look like. So velocity, I said, was L over T, and I'm multiplying that by a T. Now this T is on top. It's not V over T, it's V times T. So what that tells me, when I do this multiplication, my T on top cancels with my T on bottom, and I'm just left with L. So velocity times time is going to give me a length, or a distance. Now I can check an equation. I can say, let's say I'm going to have Vt on this side of the equation, and I am claiming that Vt equals a t squared. Now I need to know, is this true? So I'm going to do some dimensional analysis. On this side I have L over T times T, and on my right hand side I have L over T squared, and I'm multiplying by T squared on top. So on my left hand side my T's cancel, one on top and one on bottom, and on my right hand side my T squareds cancel, so I have L equals L. This equation is dimensionally correct. I'm going to give it a check mark. Now what if I had said 2Vt equals a t squared? In dimensional analysis, a number has no units, so it doesn't play into our dimensional analysis. We can just ignore it because it's a number down here. It's just multiplying. So my units on this side are still L over T times T, and on this side it's still L over T squared times T squared. So it still works out. So when I'm adding a constant to this, when I'm multiplying by a constant here, it doesn't make any difference. Now, what if I say Vt plus xt equals at squared? I want to check this equation. Now I'm adding this element of addition. In order to add things, they have to have the same units. So, for example, I can add 3 meters plus 2 meters, and that's 5 meters. But I can't add 3 meters plus 2 seconds because that doesn't make any sense. What is 3 meters plus 2 seconds? So I have to check this side. I have L over T times T plus, well, x is a quantity that's going to represent a distance. So for our length, we might have the variables x or y or h or r. All of these are going to just be a length. So a length is an L. So I have L over T times T plus L times T. Do these match? So on this, the first one, my T on the top cancels with my T on the bottom, and then I have L, which would be like meters. So I have meters plus meter seconds. That doesn't match. So this will not work dimensionally. I cannot do this because I can't add quantities that don't have the same units. So this is one way that I can check and see that my equation is incorrect. That's how we're going to use dimensional analysis. I could do the same thing with units instead of dimensions here. So I could put meters over seconds times seconds plus meters times seconds, and it would work out the same. It still doesn't work. So you can either input the units or you can input the dimensions for dimensional analysis or unit analysis.